Okay, so we're going to move on to our next talk of the afternoon, and this is going to be by Glenn Thackray, who many of you know. Glenn is a quaternary geologist, geomorphologist. He studies glacial histories, alluvial systems, active tectonics in places like the Western US, Tasmania, Wales, New Zealand, pretty nice field areas. And we're also working together in the Teton Range in the West. Glenn is at Idaho State University, where he's been a faculty member since the mid-Holocene, and that's the age that Glenn gave us for his tenure there. And he's going to be talking about glacial chronologies and glacier mass balance musings in coastal Washington, which is actually where I first met Glenn on an FOP trip on the Olympic Peninsula, which was probably early Holocene when we met. So I'm going to turn that over to you, Glenn. And anytime you're ready to share your screen.
Okay. Well, thanks, Joe. I had forgotten once again that we had met on that Friends of the Pleistocene trip, which I think was 1996. If that tells you how long I've been working out in this area off and on, there you have it. So let me see if I can share this. Yeah. Okay. So I'm going to talk about some work here that that some of which goes back a long way, some of which we keep kind of building on new data elsewhere and new ideas. And I have been talking about this stuff way too long, and yet there's just there's always something around the corner in this field area, and so. And what I want to emphasize is that the chronology that we have out here and the relative ice extent at various times is rather unique. We have it well documented, and it's rather unique. And so it may strike you as somewhat different than a lot of other places. So let's see. I am not. Oh, there we go. Not advancing, but there we go. This is a very short list of collaborators, the people I've worked directly with out there, Tammy Rittenauer, Jamie Schulmeister, some various master's students. Alan Ashworth at North Dakota State did some beetle work with us a number of years ago, and a lot of the work that has come out of these efforts is still trickling out into the literature, and it's slowly coming out, but really too slowly. And we've been a little bit remiss on what I think is one of the most interesting bits. So there are a lot of other people we could list there, but I'll move on. So the study area is out here on the west side of the Olympic Peninsula, and I have a note up here about this being an isolated corner of mountain glaciation in a Pacific world. And what I mean by the first part of that is that this area was, these were mountain glaciers for sure. They weren't impacted by the ice sheet, but the Olympic Peninsula was surrounded pretty much on 2.5 sides, I guess, by the Cordilleran ice sheet. And the Cordilleran ice sheet and the Olympic glaciers really have quite a different chronology. And what we see in the Olympics is it's almost like the Olympics don't really care about anything further east. They are looking out to the Pacific, and that seems to be the record that we get in these glaciers. So I like to think of this record as the glaciation on the leading edge. This is what the Pacific Ocean is sending inland during especially the late Pleistocene, which is most of the record we have. So that's the notion. I want to zoom in on this area, and so we're going to be looking at 3 major valleys on the west side, from north to south: the Hoh River Valley, the Queets River Valley here, and the Quinault Valley on the south end. Other areas have been studied by various people, and I won't get into that. But this area has a fairly clean record, insulated, or I guess I should say isolated from ice sheet impacts, and we can see what the mountain glaciers themselves were doing. The Olympics go up to about 2,400 meters. They're not terribly high. They're extremely wet. I don't have a precipitation map in here, but it's 5 to 6 meters of precipitation annually at Mount Olympus. So that's kind of the starting point climatologically. It's a very, very wet place. That's fairly obvious. So it is a highly vegetated area. Why in the world would anybody go out there and study this? And at times we've wondered that. But there are some real bonus aspects to this. One is there are sea cliffs that provide a transect through the glacial system. It's there's especially a section of 30 kilometers of coastline that have a lot of exposures like this one, where we can see the glacial interglacial stratigraphy. You can see a wave cut platform. You can see sand beds here, beach sands. There's some peats up in here, and then 2 outwash units above that, and an outwash unit below that wave cut platform as well. So we have some control on relationship to interglacial sea level high stands. Lots of river exposures. The valleys are deeply incised. Lots of river exposures. Some absolutely spectacular ones and some really ugly ones that you kind of have to crash through the brush to get to. Gravel pits galore. There's been a lot of logging road building out here. And so lots of gravel pits, many of them still active. The landforms are very large. The moraines in some cases are miles across. They're big landforms, and even in the days of 40-foot contour interval contour maps, we could still map those moraines fairly well. There are a lot of smaller landforms that we've picked out, of course, more recently with LIDAR, which is immensely helpful out here. We've expanded the number of ice limits we have mapped. There's wood in the sediments for carbon-14 dating. A lot of that wood is very useful to the record, except of course it tops out around 50,000 years. And there was rarely wood exactly where we wanted it. And so a few years ago, we went back out there armed with the capabilities of OSL dating, some IRSL dating, especially on the coast. The coastal sediments aren't as amenable for whatever set of reasons, which we haven't totally figured out. For those of you of the cosmogenic persuasion, all I can say is sorry in terms of boulders. In all the time I've spent tromping around these landscapes, I estimate that I've seen 5 boulders sitting on surfaces. So there really aren't any boulders to date that I have seen. And there's a lot of potential for profile dating, of course, but not many boulders. Also, a lot of organic matter, which has produced pollen and beetle records. So lots of reasons. Here's an example of a riverside exposure. This is on the South Fork of the Hoh River. The river is right down just out of the view at the bottom, flowing from right to left, which doesn't really matter. But this is a 120-meter outcrop. It's freshened up a couple of times. There have been some big falls off it about 15 years ago, which really freshened it up. There are lake sediments over here. There's diamicton in the lower left. Lake sediments. This section through here is a pile of deltaic sediments, filling in with the South Fork Hoh, feeding a lot of gravel into the system and filling that lake. And then very thick outwash, some of it small boulder size up in this bed marked 5 here, and you can see pieces of our geochronology here. This is mostly a last glacial maximum outcrop, 21,000, 19,000, 18,000 to 19,000 up here, and so we're looking at a rapid accumulation of gravel and just tons of beautiful gravel exposed here and further up the South Fork. Here's an example of one of my favorite gravel pits. And in this case, there are 2 gravel units, two alluvial gravel units, which we can link into ice marginal sequences of moraines and so forth. And there's an upper one here, which we did to 61,000 years. Notice the uncertainties on here. Some of the uncertainties are pretty broad, but we almost always get an intact sequence relative to stratigraphy and geomorphology, and you'll see some of these large uncertainties in a number of ages I'll show. And then just where this gravel pit floor here is, there's actually a thin diamicton there. And below that, there's another outwash gravel unit, which dated to about 85,000 years. These are practically indistinguishable, I think. I think they are barely distinguishable, but again, we always get that sequence pretty much with what the stratigraphy and geomorphology show us. Example of lots of wood. There are logs up here. This is an interglacial sequence on the coast. Logs up here. There's a rooted stump here, Sitka spruce stump, and so lots of material to work with. As an aside, this is actually an interglacial sequence right here, and this wood has been used in many labs around the world as an old wood standard. It's called Queets A. If you want to see a long CV, look at Google Queets A. It has a much longer publication list than I'll ever have. So anyway, that is old wood that cleans up really nicely. We have ages, reported finite radiocarbon ages as old as about 54,000 years. You can believe those if you want or not, but they actually fit in very nicely with the rest of the sequence. And as minimum ages, as close minimum ages, if we interpret them that way, they're actually pretty good. And of course, for anything younger than that, it's quite brilliant. One final bit of benefit here, and then I want to move on fairly quickly. There are paleo shorelines, and so these are outwash terraces of various ages, younger one here, an older one here, obviously. You can see the paleo shoreline right there. And then back in the hills here, there's another one that runs right along here. And so we're pretty sure that this one is MIS 5A. And that the one back in here, we don't really know, we don't have a means of dating it directly, 5C or 5E almost certainly. And so we're looking at a last interglacial to latest Pleistocene sequence in these sea cliffs and in the river exposures. So let's talk about the LGM first, so I'm sure to get to it. The LGM in this case is way up the valleys. 40% of the glacier length is represented by the LGM. The earliest, the oldest ice limit we see in the Hoh Valley is out here right near the coast, and it's about 90,000 years old, we think. And here's the LGM. There's a great sequence in these two papers with Siana Wisnitsky as the lead author, describing this sequence in the South Fork Coates. There are three ice marginal sequences from the LGM period, 22 to about 19,000 years, and really a lot of brilliant stratigraphy in there. I want to focus in a minute down here on the Quinault, where these moraines outline a very large Piedmont glacier, and we have a really nice luminescence chronology from that area. So what is all this stuff downstream? I love this. I really kind of only discovered this recently, that the scale of this set of moraines here is very similar to the scale of the Malaspina Glacier. So these moraines are representing a mid-latitude Pleistocene version of the Malaspina Glacier. The scale is almost right. The two glaciers coming together is almost right. It's like the spitting image. The ocean is right there, etc. So as an aside, that's kind of what we're looking at with these moraines. I want to call your attention to the scale. These are, here's 10 kilometers. And so we're talking tens of kilometers across and right about that right scale. We have a lot of radiocarbon ages, a lot of OSL ages. The radiocarbon is mostly published. The OSL is largely not published yet, except for the South Fork of the Hoh. We have some old TL ages, which didn't work out very well. And then Daryl Kaufman and I years ago got some amino acid racemization age estimates out of some glacial marine sediment. So lots going on. 12 defined ice marginal landform sediment sequences in these valleys in sum total. Not everything everywhere, but that's what we see. And each of those 12 is represented by a sequence of landforms and in most cases a sequence of sediments that we can define in outcrops, be they in gravel pits or be they in river cliffs or sea cliffs. Here's an example of luminescence dating and the possibilities that it opened up. There's a glacial diamicton across this. There's a moraine just down valley. This is in the Quinault Valley. This is on a FOP trip about 2015, I think. And in the gravels, so we can exploit these ubiquitous gravels and get the sand out of the gravels and get ages that pertain directly or that are near maximum ages on the diamictons, and those ages have worked out quite well. So keep that 56 in mind because it's going to show up on the map. That 56 Ka age is here. We have a 50 Ka age associated with the same sequence up here. And so here in the Quinault, that broad Piedmont lobe extended out on the coastal plain. And we have a nice sequence of ages. Notice that they aren't perfect and that the uncertainties are large. But out here at the coast, these are in buried sediments. They're associated with the red and pink color here, even though the landforms are the brown. That's just overlying. And we get ages over here of 107 and 102,000 years, 103,000 years on the same sequence. Out here, this is the surface age. I misspoke a moment ago. That's 67,000 years, 70 there. We're in the 50s in these greens. We step into 45,000 here, and then buried here we have a 65,000 year age that's hard to link out here. But then this gray or this tan color here is an LGM era moraine right at the edge of Quinault Lake. So lots going on there. So here is the summary of all that geochronology. This is each of the three valleys, and again, some of the ice advances are documented in some valleys, but not others. Others we find across the board. Here's the summary, putting everything together. And those are those 12 advances that I talked about. We think that red one, that one shown in red on the map, is probably somewhere around MIS 5D. The purple, which is in the Queets Valley especially, and the Hoh Valley, 5B. And really, a lot of the story is in MIS 3. Those are the three MIS 2 events. And the real action, the big glaciers, the multiple advances are in early and late MIS 3. All right, why? Why did all this happen? Well, decades ago, Steve Porter looked at the elevations of cirque floors across the Olympics, and he found that the modern glaciers have a profile that declines gently west. But the lowest cirque floors, composite Pleistocene glacial features, descend steeply to the west. And that implied to him and to me still implied a deflection of the mass balance profile to the west. And that incorporated a lot of these lower peaks in the Western Olympics into the accumulation area. And that is really that is how these built up so big, in my opinion. And of course, everything would be happening more aggressively in the high country as well. So that extends the accumulation area way far west, and so these valleys were able to fill with ice from the high country and presumably being fed in from this lower terrain. Paleoecology has proven quite interesting, especially the beetles. There are beetle records here, some around 40,000 years, some from the LGM. And this is from a paper, and I misspelled Alan Ashworth's name there, sorry about that. 2020 paper in a GSA volume. And really the beetles show modest cooling during those earlier advances, about 4 degrees cooling from modern during the LGM. So there was cooling, not a lot of cooling, but in these very wet places, as long as the precipitation keeps coming in, they're very temperature sensitive, and a lot of rain gets converted to snow with a modest bit of cooling. So 4 degrees may have been enough to build those glaciers. There's a lot of work left to be done on this. There's some mass balance modeling that can be done, but at this point, those are my musings on glacier mass balance. The cooling is kind of interesting, especially with this recent paper by Maureen Walczak, I think is how you pronounce her name, having to do with marine cores in the Northeast Pacific. And they found IRD spikes around 43,000 years and around 30,000 years and around 25,000 years, and then in the 15 to 20,000 year range there, and speculated that that Pacific events actually may there are Pacific ice rafted detritus events, and they may have preceded Heinrich events, so implying a possible Pacific control. One of the observations I've made quite a number of times is that the record here in the Olympics is more similar to a lot of areas of the Pacific than it is to a lot of areas of North America, and I'll leave that part right there. The other question is, why don't we see these in the interior? We don't really see them in the glacial chronologies, but we see events of 36,000 years and 45,000 years and so forth, especially in alluvial fans, and also in a lake chronology down here that Willie Amadon has derived, and a few other places, isolated moraine boulders, and that's about it. So they did impact this area, I think, but the LGM was a much bigger event around here. So in the glacial systems, it overrode that. So I'm going to leave you with this set of questions and a few answers, and leave it open for questions. All right.
Thank you, Glenn. Thank you. Lots of interesting stuff to talk about.
All very quickly.
Yeah. So, but we have time for questions, and looks like Cal has his hand raised.
Thanks, Glenn. That was great. Another great presentation. You used the term more extensive. Would you say that it's more extensive, or with subsequent glaciation, the ice volume is more topographically confined?
Topographically confined within the valleys.
Yeah, so it's getting there's, with subsequent glaciation, there's more and more topography to hold that same ice equivalent volume each time, so it doesn't go out as far board.
Right. Well, that's always a question, especially in a tectonically very active origin like the Olympics, and I think what I have for that is no real answer that is particularly worthwhile, because it's a very hard thing to constrain in these particular valleys. What the former valley margins were. However, the changes in ice volume, the contrast in ice volume that we or of extent, let me use extent rather than ice volume, it's happening over the course of tens of thousands of years. Now, in the Olympics, with rapid uplift and fairly erodible bedrock, are those tens of thousands of years intervals between glaciations, is that enough to or is there enough time under ice there, let's say, to do that erosion? And I would think that we definitely see that effect over time scales of a couple 100,000 years. But a lot of this shift we're seeing over the course of a few tens of thousands of years. So that would imply a lot of accommodation, valley accommodation space, if you will, being created fairly quickly. Big glaciers, big warm-based glaciers, probably very fast moving in the gray wackies of the Olympics. We might have to shift our scales of erosion at that point.
Yeah, no, I mean, it's a great scenario, and those those 107 and 102 ages that you had right out on the coast.
Mm-hmm.
It looked like from that MIS 6 to 5 pretty much covered the whole area. Was like, is there older drift, remnants of any older drift, or did like 6 and 5 kind of cover that the whole area?
Well, yeah. So we used to think we had MIS 6 nailed down, and maybe some much older sediments. That was based on some very weak paleomag measurements about 30 years ago now, and when we went back with luminescence dating, we got very nice ages. We do have MIS 6 in one location beneath that wave cut platform. One of those outwash units beneath the wave cut platform is about 125,000 years, and so we do have MIS 6 in at least one coastal exposure, one area of coastal exposures, and that's as much of an older record as we got. What we learned through luminescence dating is what we used to think was MIS 6 and earlier was only as old as MIS 6 and everything and a lot of younger material, and that has been borne out through the luminescence dating on a whole sequence of outwash and associated units.
So the one is the 102 and the 107, those ages on those on your map, are those on outwash or till?
107 and 102 are on outwash specifically. Pretty much all of the luminescence ages are on outwash, because that's what we have some confidence in. There are also some sand beds in lacustrine sediments.
And those overlie the 125 age that you have?
Not directly, but they do overlie
till
an erosional surface on bedrock at that location.
Okay, so that's like the deglaciation of MIS 6.
Yeah, or it's a 5D glaciation.
Or a 5D, yeah.
No,
Got it.
And we don't really know.
No, just lots of morphometry to play with over there. It's exciting.
That's right.
So Keith has his hand up. Keith, you want to go ahead and jump in?
Yeah. Well, both talks I appreciate. So thank you. Glenn, maybe I missed it. The beetles and then your temperature depression inferred from those beetles. What age is that?
That is specifically LGM. Or very close in a sequence of organic matter spanning the LGM, primarily at a place called Glacial out on the coast, where there's an interglacial. It's an area, a pocket between the two glaciated valleys. So there's no outwash in there, and there's a long sequence of silt deposits with a lot of peat in them. And Cal Heuser decades ago got a pollen record out of there, and more recently Alan Ashworth and a grad student back in the day got a beetle record from about 38,000 years ago out of there, and then more recently an LGM, roughly LGM record. So
is that an annual temperature or summer, winter? What?
That's mean annual temperature.
Okay, because it seems your operative word was modest, and it does. And what surprises me is the way you described. You have the Cordillera wrapping around, right? And I would think it would be cooler, but maybe does the water or proximity to the ocean moderate temperature? What's going on there?
It has to be moderating the temperature, and even in the Puget Lowland, what's the story? There's at Discovery Park in Seattle, there's the Olympia interglacial beds or interstadial beds get up to about 17,000 years. and there are beetle fossils in there that Alan has worked with. And they show that the temperature, even as the ice sheet lobe was advancing from the north, the temperatures in the Puget Lowland were it was apparently cool but dry, but not utterly frigid. And it is low elevation, right? So it should be a fairly moderate climate, but at the time the ice sheet was still advancing to its maximum, the Olympic glaciers were already retreating. And that's why we think that they are, and remember, the ice sheet is dealing especially with accumulation to the north of where we're talking about. But it doesn't seem to have gotten particularly cold at that time, at the time that the Puget Lobe was and the Juan de Fuca lobe were surrounding the Olympics on 2.5 sides. So it really seems to respond to, it seems to be reflecting the moderating influences of the Pacific, especially.
So one other quick thing, has anybody looked like a quick and dirty lapse rate with cirque floor elevations or ELAs?
Well,
certainly the moisture is going to complicate things, but
right. In fact, we should, if we look at lapse rates, we pretty much have to look at a lapse rate for fairly moist conditions, obviously, and there are some studies that have come out of various places looking at the effects of lapse rates on glacial mass balance, and how humidity tends to change that lapse rate and how that may affect glaciation, because it really is a matter of in this case rain to snow conversion. So if we have 5.5 meters of precipitation per year, and that precipitation can still get in there as it cools slightly, that lapse rate shift ought to have a big effect for a modest degree of cooling. And those are things that need to be played with, but it has to be an adjustment of the lapse rate that helps it along. So I think you're right on it there.
Thank you.
Mm-hmm.
Okay, great. So we're at 5:03. We should probably wrap up here.
Mm-hmm.
Thank you again, Glenn, and also to Laura, who had to hop off the call. Before everybody splits, just a reminder of what's coming down the pike next week. We have another 2 talks, and we're going to be on Thursday next week, and we're going to have a talk by Aaron Barth on the Barrett-Tooth Mountains, and then Jordan Dahl and the Great Basin. So hopefully you can all tune in for those talks next week.
Hey, could I quick just send my apologies? I have to get my car repaired tomorrow on next Thursday. So I may be here, but maybe not.
Well,
so apologies in advance.
Apologies accepted in advance, but Ben is recording these, so we'll have archives, right?
Yeah,
so that's
good.
The beauty of that, and we'll be able to not miss any talks that way. All right, great. Great to see everybody. Hope you all have a good Friday. And let's keep up this tradition. This is awesome.
Yeah. Thanks, guys.
Sounds good.
Thanks for coming. Thanks for organizing.
Yep.
See you soon.